So in this video I'll be covering a series of tutorials, and what I will be covering will be related to the three-phase induction motor, and step by step I will be talking about numericals related to topics of how to find synchronous speed or NS of induction motor. Then I'll talk about how to find the slip of induction motor, which is given by S, and then I will talk about the torque of induction machine. So the different kind of torques, like the starting torque, which can be given by Ts, and the maximum torque, maximum starting torque, which can be given by Tsm. And then I will talk about a lecture or numerical about the finding of the running torque of the machine. So the running torque can be given by Tr, and the maximum running torque, which can be given by Trm. And then I will talk about a numerical demonstrating how to find out the power in induction motor. So the power which I'll be talking about, the power generated and the power output, and how to find the efficiency and the torque based on the power, torque at the output based on the power, or how to calculate torque based on the power. So these will be the different topics I will be covering and in this lecture. So it will be close to 30 to 50 minutes approx. Since I am starting now, I don't know how much time will it take, but this could go up to 50 minutes or 1 hour, and I will cover all these two topics listed here, starting from how to find the synchronous speed, slip, and the torque, and the different kinds of torque, and how it is related to the power and the equivalent circuit of the induction motor. So also I will be talking about the equivalent circuit calculation. So these all are in the numericals or based on examples or problems. So you could go through each of them or whichever topic interests you, but I will be taking till here what all topics I will be covering. I will be taking it from one single example or one example of numerical. So if you are looking for these topics, then you could view the video to the full length to understand the topics. So the machine which I want to talk is, this is again not based on any practical synchronous or induction machine. This is only for demonstrating calculation. So the question is, the machine is having a synchronous speed of 1000 rpm. So the details are given here, and the frequency is equal to 50 Hz, and the number of poles is equal to 6, and this is a three-phase machine it's a induction motor, which is a three-phase induction motor. And now the question is to calculate, and the slip given is 0.06 when the machine is running. So the first thing which I want to calculate based on this is how to calculate the synchronous speed, or ns. So ns is already given, which is equal to 1000 rpm, and ns in rps can be given as 1000 divided by 60, which is equal to 16.6. The next thing is based on your ns. So suppose your ns is given, at the same time your poles are not given. So how to find poles based on this is question 1, is to convert it to in rps. So this is a synchronous speed in rps, and the second question is how to find the poles if it is not given. Well, it is given as 6 poles here, but if it is not given, then based on ns. So it is ns is equal to 120 f by p. This is the equation for the synchronous speed. So based on this, if your ns is 1000 into 120 into 50 divided by p, 120 is equal to, so this will give a calculation which is equal to your poles is equal to 6 based on this, if you will solve for this. So it is possible to calculate your poles based on your synchronous speed. And next, suppose your this is a question third, and your slip is given as equal to 0.06. Now how you will calculate your speed of rotor shaft or running speed of the machine. So it's simple to calculate, and the method is very simple. Like, your speed can be, your slip is given as is equal to ns minus n divided by ns. So this is the formula of slip. So based on the formula of the slip, it is can be given as 0.06 is equal to ns, which is equal to 1000 minus n divided by what is equal to 1000. So this comes, when you will solve this, your n comes close to what is 1000 minus 60, because this if you will multiply it will give 60, and your n is equal to 60 or 940 rpm. So these are some more things which you have found out so far. So this was all about, and if I just so your slip is given here, and your n was equal to 940. So your frequency of the supply current is equal to 50 hertz, but the frequency of your rotor current will be what? So the next question, the question 4, is to find rotor current frequency. So F art can be given as equal to 0.06, which is slip into F, so into 50, so which comes close to 3 hertz. So this is your rotor current frequency. So based on whatever is your frequency of your supply, it's possible to define the frequency of the rotor current. Now if I'm adding some more details to the same question, like if my rotor resistance of the A phase, so if my rotor is connected in a star, so if these are the 3 windings of my rotor which are connected in a star, then the RA, RB and RC. So this I am talking for a slip ring motor. So it's possible to bring this out and connect 3 external resistance to this circuit. So it's possible to have such kind of a arrangement when you will call it as a slip ring machine. So my RA is given as 2 ohm while my XRA is given as 4 ohm, and my voltage is equal to 230 or 200 or 100 voltage, which is line to line voltage, or 100 voltage, which is a line to line voltage generated in the rotor side per phase. Or if you can add this in such a way that this is your per phase voltage generated in rotor. So now the question is to find the IRA, that is a rotor current induced in rotor per phase. So this is my question 5, and it is to find IRA. So now how you will solve this is, the first step is to find the ZR, which is my rotor impedance per phase, and which is equal to 2 square plus 4 square, which will come close to 4.47 ohm. And my rotor current per phase, which is developed, and if you're considering it measuring between the two lines, it will come cross to divided by root 3, which is equal to 57.73 volts. Now this is per phase voltage, and your current per phase, if you consider your A phase, it will be 57.73 divided by what is 4.47. This comes close to 12.91 amperes or ohms. So this is the current per induced per phase. Now the next question could be, the current comes close to 12.91 ampere. So your IRA is close to 12.91 ampere, and now the question is, this is your starting current at 12.91 ampere when your resistance at starting is equal to 2 ohm, and these are the conditions when I'm considering the open circuit at rotor end. That is, the 3 leads which I am bringing out is not connected through to the slip ring. Now if I am adding an external resistance at the time of starting, such that if I am adding a RSE such that it is equal to 10 ohm, then my impedance will become, this is again moving ahead. So now the question 6 is, if an external resistance per phase is added, then what is the starting current per phase? To find out this, so now if I am adding, then my impedance will become equal to under root of your resistance will become equal to 12, and it will become equal to 12 square plus 14 or plus 16, which is 4 square. So under root of 144 plus 16 is equal to 12.64. So your impedance now is equal to 12.64, and your starting current IR is equal to 57.73, which was equal to your voltage per phase divided by 12.64, which is equal to 57.73 divided by 12.64, which is equal to 4.56 amperes. So now it is seen that by adding a external resistance of 10 ohm at the time of starting, it's possible to reduce the starting current. So earlier my starting current IST was equal to 10 or equal to 12.91, and now it is IST2 is equal to 4.56 amperes. So it is possible to show that while you're adding your starting resistance, your current is the current at the time of starting is getting reduced. So now what will be the effect of torque on this? So the question 7, for the same parameters or the same details, it's possible to show that the torque is maximum at start when your resistance of rotor per phase is equal to the inductance or the reactance of rotor per phase. So in this case, whatever was your detail, if you are taking that into consideration, then your resistance Ra per phase was equal to 2 ohm and your reactance XAR was equal to per phase was equal to 4 ohm. So this was two details which you had, and now considering this, if you are adding a RAE, which is external resistance, is equal to 2 ohm, then my resistance or total impedance ZAR will become equal to 4 plus J4, which is equal to under root of 16 plus 16, which will come close to what is 5.65 ohms. So this is what is my impedance at the time of starting, or this is the impedance for to get the maximum torque at starting. So the equation of torque or the starting torque can be given as 3 divided by 2 pi ns. So this is for considering all the phases, and you are considering that you are having identical phases. So whatever values is valid for one phase, it is also valid for the other phase, divided by ER square, which is the rotor current square voltage square, into RR divided by RR square plus XR square. So if you're considering for a phase A, you can take the phase A values here. So your TS will be equal to 3 divided by 2 pi, and your NS, which was equal to 16.66 if you are considering it in terms of rotation per second, this is in RPS, into your ER, which was equal to 57.73 whole square, divided by into RA, which is equal to 2, divided by, or RA, which is now equal to 4, divided by 4 square plus 4 square. This is equal to, when you will solve for this, you will get this part, you will get something like 0.0286 into 57.73 square. So 50.7.73 square into 4 divided by 16 plus 16, which is equal to 32. So you will get a starting torque of close to something like a 9.551. So this into 57.73 whole square into 4 divided by what is 32. So this comes close to 11.91 Newton meter for this motor. So this is what is my torque, which was at the time of starting. This is the maximum starting torque possible for this configuration of the machine. So what is my torque without any added resistance? So that will be equal to TS is equal to, if we call the TS1 equal to 0.0286, which was my K into 57.73 whole square into my resistance, which is 2 now, and whatever is here, it is 4 plus 16, which is equal to 18. So if you can cancel that, this is 9. So that will come close to 0.0286 into 57.73 whole square divided by 9. So which is equal to close to 9.5316. But so this is your torque with no added resistance. So but now the big question that comes is, the torque has increased only by a margin of something like, for this motor, if you see this 2, then the torque has increased only by a margin of something like a 3, or if you calculate it accurately, it was 11.91 minus 9.5316. So it has increased only by a margin of something like 2.37 Newton meter. So is it only to increase it by a margin of this that you have added the external resistance? The answer would not be that, but it would be that there would also a considerable reduce in your starting current. So if you would have seen previously what your starting current was, your starting current without any resistance was equal to 12.9 amperes. Now if you will calculate the starting current in this case, or in the case where you added the resistance, it would be IR per phase is equal to VR, which is 57.73, which is divided by your ZR. Your ZR here comes close to what is, when you're adding the resistance, it will be 16 plus 16, so it is 5.65. 57.73 divided by 5.65, so that is equal to 10.21 amperes. So there is also a reduction in the starting current. So there is a reduction in the starting current which is close to 2 amperes or 3 amperes which you are getting, and at the same time, while there is a reduction in the starting current, there is also an increase in the starting torque. So this is a configuration which is possible to get the maximum or to get the maximum amount of starting torque when your starting resistance is equal to the XR. But again, the other case which I considered previously was by taking a starting resistance, or by taking a starting resistance, if you can say RST, which was equal to 10.21 amp, or a starting resistance of 10 ohm. So So my resistance RSA will become equal to 10 plus 2, which is equal to 12 ohm. At that same time my starting current was equal to 5.7 amperes per phase. So, and my starting current ISA in the condition where there was maximum torque production was equal to 10.20 amperes. And if you are again considering what was your torque here, T max was equal to close to 9.5 Newton meter, and your T max at still without any no added resistance was equal to something like, or this was your T max without any added resistance. So this will come here, and what was it without? It was close to 11 or 12 if I am correct. So 12 Newton meter, which was around, which was calculated. So but what will be if it is, while at this time when you are getting a current or IST which is equal to 5.7 amperes, which is a very low starting current. So what will be your torque here? So just to check that your starting torque will be equal to what is 3 divided by 2 pi ns into ER, which is 57.73 whole square into 2, or into 12 in this case, and 12 square plus 4 square. So that will come close to 57.73 whole square into 12 divided by 12 whole square plus 4 square, and into of what is like, what was it, 0.0286. so it comes close to your starting torque in this case is close to 7.14, so which is again less than your this one. But your maximum torque, at the maximum torque you are getting current close to 10 amperes, while here while you are getting a current close to 5.7 amperes, your torque is 7.1 Newton meter. So there is a reduction in torque. So it is seen that the optimum is obtained when your RA is equal to XA. So that was the case when you got 10.2 amperes current and you got a torque close to 12 amperes. And this case, to not to get confused, this is a case when you are starting the motor. So, and again this is a case when my motor is slip ring induction motor. While the case if this was only my squirrel cage motor, I would not have been possible to get any addition in the starting torque. In that case my starting current would have been at whatever value, and it is close to 9.5, and the starting current would have been close to 12 amperes, which was found out. So there would have been no possible change possible. But while you are having a slip ring induction motor, it is possible to add a RAS or external resistance per phase using the slip rings, and it is possible to increase the resistance, and it is possible to vary the torque and get a maximum torque also, and it is possible to get the different configuration of the torque also to reduce the starting current if that is the main requirement, or to increase the torque, that is the main requirement. So both are possible by using a squirrel cage induction motor. So now coming to the next question, adding on the same thing. So till now what we have seen is, we have seen about the starting torque or the starting torque condition of the motor. So this is what we have seen now, and my TSA is what is my starting torque for phase A, considering the parameters of phase A, which I am again multiplying it by 3. So this was my starting torque. So now it is to see what is my running torque or TSR. So now considering a case where my slip is 0.06, and now what will be my slip has been reduced is 0.06. So the change will come in my voltage. So my voltage of the rotor will be multiplied by E. So and the frequency of the reactance per phase will be or the reactance will be multiplied by a S factor or the slip factor. So again my equation of the running torque TSR, which will be equal to what is like 0.0286 into the voltage is like 57.73 whole square into my slip, which is equal to 0.06, and since I'm not adding any external resistance, it will be multiplied by 2, which is a R, and your R square, which is 4, plus 0.06 into X, which is equal to 4 of whole square. So my starting torque in this case will be 57.73 whole square into 0.06 into 2 divided by 4 plus 0.06 into 2 and into 0.0286. So my starting torque, if you'll solve for this, it will come close to what is 2.78. So this is a torque produced by the machine when it is running, and when my slip is close to 0.06. Now the next question is that how to produce a maximum slip, or when is the maximum torque produced when my motor is running. So for that the condition is very simple, and it is something like this. So the condition is like when your reactance is equal to, or the maximum slip is produced when slip is equal to RA, rotor resistance per phase, divided by reactance per phase. So if you are designing your rotor in such a way, or if you are adding external resistance in such a way to make this possible, so that your RRA is equal to 4 in this case, or slip is, you are making your motor to run at a slip is equal to this, so equal to 2 by 4, which is equal to 0.5. So when my slip is equal to this value, then my maximum running torque will be produced. So again, when your slip is equal to 0.5, what is your speed? So your slip is given as equal to ns minus n divided by ns. So what you will get is 0.5 is equal to 1000 minus n divided by 1000, which is equal to my n is equal to 500 rpm. So when your machine is running at, or motor is running at a 500 rpm, you will get a maximum torque production. So there is a reduction in speed which is seen. While my slip was equal to 0.06, my speed was high. So again you can see, as your slip has increased, your speed has reduced, but at the same time at this slip the speed was equal to close to 950 approximately, and at this slip whatever this slip was equal to 0.06, and whatever torque was being produced was close to 2 point something. So it was a very low torque, while your starting torque was close to 11, which was maximum possible, 11.8 which was maximum possible approximately, and this was close to 2 which was maximum. So again, to produce a maximum torque at running, you will need a slip which is given by this equation, and that is close to a 0.5 slip which you are getting, and the speed is 500. So there is a reduction in speed which is happening. So that's one other observation which you can have. And next, calculating the slip at this. So to calculate the slip T max can be given by two formulas. One is, so taking the previous formula which we had, so it is 3 divided by 2 pi into 16.66 into 0.5 into 57.3 whole square into 2 square divided by 4 plus 0.5 into 4 whole square. So this is equal to 0.0286 into what is 0.5 into 57.3 whole square into 2 square, which is equal to 4, and divided by under root of 4 plus 0.5 into 4 whole square. So you'll get a slip close to, if you are substituting it, you'll get a slip close to what is 11.76 Newton meter, and your slip running at your torque at 0.06 was close to 2.7, while your maximum running torque at a slip of 0.5 is equal to 11.76 Newton meter. So there is obvious increase in the running torque, while your starting torque maximum was close to 12, and it is very much close to what is your maximum running torque. So again, if you see the torque slip curve, if this is your slip of 0 and if this is a slip of 1, then for different, it is possible to have a curve something like this, where you will have a maximum torque in this case which is equal to the slip of 0.5. you will get a maximum torque, and beyond this, if you try to run this machine, it will be called as the pull out torque, and this is your starting torque at a specific resistance. So it is possible to increase this by increasing your resistance. So if you are increasing it to 2 times, then it's possible to increase whatever your torque you are having here, or whatever torque you are getting. So this is when you are starting, your ns is approximately equal to n, so your slip will be equal to 1 or approximately equal to 1. But as you are running it, as you can see, when you have come here, your speed was reduced to 500, so here your speed was 1000. So there is also a reduction in speed as you will go in this direction. So if you'll plot this graph for different slip, it will look like something, and exactly it can be found out by substituting the different value of slip in this equation and plotting it against the torque. So that will give you the T versus S curve for a machine. So that is how the torque and the slip is related. So the next one more question I am going to add is related to what is my this was related to my torque slip characteristics and related to the starting torque, the running torque, the starting torque which was maximum, and the running torque which was maximum. So what we found out is that your starting torque is maximum when R2 by X2 is equal to S, and your running torque, or this was for your running, and your starting torque is maximum when your R2 is equal to X2. So this is obviously two things what we saw, and again the equation of slip, the equation of frequency related to slip, and ns is equal to 120 f by p, and s is equal to ns minus n divided by ns. So this was the different things which we saw and calculated till now. And next I will talk about the approximate equivalent circuit and the problem based on that. So this is related to a approximate equivalent circuit. So if you have a if you are having a motor which can be given by this circuit, which is a per phase, again so this is your R1, that is a rotor resistance, or the stator resistance. This is a X1, this is a stator reactance. This is your supply voltage per phase, and this is a Xm is equal to the magnetizing reactance, which is for supplying for the current which will be used for producing the magnetic field, or the part of the magnetizing reactance. And this is your rotor resistance for A phase if you are bringing it to the stator side, and this is a rotor reactance for A phase if you are bringing it to the stator side, and this is a variable resistance which can be shown as related to your slip, or the rotor resistance for A phase into 1 minus S divided by S. So based on this, now the question is to calculate what will be my power input, what will be my power output, and what will be my torque output. So this is a different machine which I will be taking, so the details will be different. And so just bringing in the details, what you will have is if your R1 is equal to 2 ohm, your RAR dash is equal to, or this is equal to 0.2 ohm, and this is equal to 0.4 ohm, and your x1 is equal to 1 ohm, and your x2 dash is equal to 0.4 ohm, and your xm is equal to 20 ohm. And the machine is a 600 volt machine, This is a 6 pole machine. It is 600 volt, which is a line to line voltage. And now the question is to find the power at the gap, or the power transferred across the gap, the power output, the efficiency, and the torque developed. So if you are given such a question, and the frequency is equal to 50 hertz, and this is a three phase machine. So the first step is to find your resultant impedance. In this case, it will be equal to 0.2 plus j of 1 plus of j of 20 for the parallel circuit, and into 4 plus j of 0.4 divided by 4 plus j of 20 plus 0.4. So this is what is your impedance, and when you will solve this, it will come close to something like a 4.639, making an angle of 27.25. If you are, I have already done the practice on my book, or I have already worked this out in my book, so when I will solve it, it will take at least 10 or 4 to 5 minutes to solve this, and you will get that in a way. And it's possible to show that this part, which is the part which is for the power which is transferring across the gap, it will be equal to something like a 3.7023 plus j of 1.118, or 3.77 into j of 113. So this again, if you are solving it, it will come close to 0.2 plus j of 1 plus 3.7723 plus j of 1.113. And the reason is that if you liquid this, it will come close to this. So this is how we are finding your ZR. So based on your ZR, your IA, or the current per phase for the phase A, will be, your voltage will be, VA will be equal to, considering the phase voltage, it will be equal to 600 divided by root 3, which will come close to 346.41 volts, and your IA will come close to 346.41 divided by 4.639, which was your this, and your angle will come close to, which is the angle is of 27.25. so it will be moved, if you are moving it up, your IA will be equal to something like a 74.67, making an angle of minus 27.25. so this is a lagging power factor, which is for the machine, which is equal to this. So Now the power, if you are calculating the total power input, which will be equal to root 3 into, which is per phase, into 3, or it is equal to 346.41 into 74.67 into cos of 27.27, which is a power factor. So this will come close to what is equal to 68987.14 watts. So this is how you can find the power input per phase. So again, to find the input per phase, what you have done is you have multiplied it by root 3, so you are getting the line voltage here. So you are multiplying it by 600 here. So that will be when you will getting a value here, and this is multiply it by root 3 to convert this into the line voltage. So this is a power, line to line power output. If you are multiplying it by 3, you will get the total, if there is a 3 phase output. So if you are calculating the per phase value, then this is a value per phase, since we are only considering the power input per phase, because all our values here, if you see the impedance or the resistance, everything is considered per phase. If you are multiplying even this by 3 and then you are considering all the values, then you will have to multiply it by 3 here, so that will give you the total power input of 3 phase. But since you are considering only per one phase, and since the power which you are giving the line to line, which you are considering, this is my line current IL is equal to root 3 into IA, and this is your line to line voltage, which is VL, which is equal to VPH by or into root 3. So that is giving your line voltages and line values, and you have calculated your power close to this value. Now the big question is that what is your power input is equal to, what was found is equal to 68987.14 watts. This is per phase. So what is your power developed? Which is equal to 1 minus S into P, or power which is transferring over the gap. So if you would have seen the equivalent circuit, it was something like this. There was an impedance here Z, which is, you can call it input, and then there was IM, and then there was a circuit for the rotor ZR dash, and then there was a resistance of rotor which was related to the slip by this. So whatever the power you are transferring is the power which is across the gap. So first you have to find the power which is transferring across the gap, and that can be found out by the power which is getting over the reactance, which is of this, or the resistance part of this. So you're considering the active power only here. So your whatever you are calculating is in watts. So this is only for the active power. So whatever, if you consider the equation of the impedance, which was written as 0.4 plus J1 plus 3.77 plus J1.113. So the power across this resistance will be your power across the gap. So P across the gap is equal to 3 into 74.67 whole square into 3.77. So again this is by considering it for the three phases. So you are multiplying it by 3. So there was just a mistake in whatever values. If you'd have noted a mistake, it was very much evident that whatever power input we have found out is for three phases rather than line to line, because it was multiplied by root 3 into V line into I line into cos of phi. So root 3 of IPH will give what is your line voltage, and this was also for your phase voltage again. So it was divided by root 3, or this was 3 into VPH or V line divided by root 3. So this was how you are getting the root 3 here, and that was how you found out your input. So that's how I calculated that, right? But I just missed that while explaining. So this is not a big deal of mysteries, but so now what is this? And when you will solve this, it will come close to 63,009.475 watts, and this is your power which is transferring across the gap, and your power developed is equal to 1 minus S into PGAP. Your slip is equal to 0.05, so 1 minus 0.05 into 63009.4, which is equal to 58858 watts. So this is what is your power developed. So your efficiency is equal to your power developed, which is equal to 58858 divided by whatever was your power input, which was equal to 68987.14, which was found. So your efficiency come close to 85% for this machine for the specific configuration. So again, just to tell what was, so your power developed was equal to 1 minus S into PG, which is 1 minus 0.05 into 63.009 kilowatt, and this has come across 59.85 kilowatt. Now your power out at the shaft, or the power available at the shaft, is equal to whatever is this 5985 0 minus of what is my 800. 59850 minus 800 is equal to what is equal to 59050 watts. This is your power which is available at the shaft, which is you are minusing 800 in this case, or you're minusing 1000 in this case. If I'm considering 1000 is equal to whatever is my fixed losses. So this is the fixed loss which is happening as part of the core loss or iron loss component plus your mechanical losses. And your efficiency was calculated based on this. So this is 58850 and the efficiency was calculated based on this was close to 85%. So that's how you can calculate based on equivalent circuit. So just to summarize, so whatever values the voltage which I have given is equal to 600 volt. This was my line to line voltage, and when I am converting this to phase, it will be equal to 600 divided by root 3 is equal to my VPH. Now I had the values based on which I calculated the equivalent impedance, which was again per phase. So my IPH was equal to VPH divided by ZRPH. And what this gave me my IPH, and this also gave me my IPH, making an angle of phi. And it gave me my phi is equal to my power factor angle, and this was also per phase values. So my power input was equal to 3 into root 3 of IPH into V line or which is equal to IPH divided by root 3 considering the power input. If you are considering it to the per phase, it will be VL divided by root 3 and into cos of phi. So this was your power input total, and then your power developed was equal to 1 minus S at shaft was equal to 1 minus S into power across the gap. This was the power developed at my rotor, and now my power output which is available at the shaft to do work, this was equal to P developed minus of fixed loss, and Then I found my efficiency is equal to P output divided by P input. And now it's also possible to find the torque at shaft is equal to P output divided by omega s. Or so this equation you can use to find your torque. So this is whatever we have calculated so far in this problem, and this is how you can proceed to calculate. So in this case the fixed loss was equal to 1000 watts was given. So it's possible that it's not given, or it's possible that you will have to ignore the iron loss component. So again, another possibility is that you are drawing the circuit, the equivalent circuit. There could be two components. One is the RC, which is for the core losses or the iron losses, and the other is the magnetizing component. And then you will have the two components and also the resistance. So this is R1 X1, this is XM, and this is IM, and this is RR, and this is XR, and this is a variable component. If this is, which is variable by according to the slip given by 1 upon S divided by S. So if your slip is varying, this will vary, but considering that you are keeping your N is equal to constant, or your torque is equal to constant, in such cases what will happen, your N will not change, it will remain same. So your RR component, or your this into 1 minus S by S is equal to, you can take it a RR dash, or R dash will be, if you are writing this as equal to R dash, then this will be constant. So your power developed across the gap is always found out as the active power, and that power is the power input into whatever is my resistance, which is RR dash plus R of RR dash. But in the case where the RC is given, suppose it is given as a 1 ohm or whatever, in such case you will have to first solve for a parallel. So you will get an impedance of ZRM here, for example, and then you will have to solve this full circuit as so you, in that case, you will have a ZRM here, for example, and this will give you your, this circuit will be in parallel, and this will be used if you are getting an equivalent impedance of ZR in that case. So your IR will be equal to VPH, or IR per phase will be equal to VPH divided by ZR. So in that case, when your iron loss component is given as some part, so if this is given as 1 ohm more specifically, in that case if it is not given, it might be ignored, or in the case which it was, in our case it was a value which was 1000. So if I am again seeing my power developed was equal to 5985 kilowatt, and my power output was equal to 5985 minus of 1000, which was equal to my fixed loss, and this comes close to 58858 kilowatt or watts. So if even if you are ignoring this, if it is not given in the question, sometimes it's possible to ignore it. There is not a much difference in uh, my machine, but what difference will it have in calculating my efficiency? If I will calculate it based on my power developed, then my efficiency will be equal to 5985 divided by 6898.14. So my efficiency will be equal to 59.5985 divided by 6898.14, so into 100, which comes close to 86 percentage. So without considering the constant losses, or this part which is my RC, and also the vintage and friction losses, which was close to 1000, which came close to 1000, without that my considering that my efficiency was 85, so even by considering that, there is only efficiency difference of 1 percentage. So sometimes it's possible to totally ignore this component or the fixed losses and only consider the constant or the copper losses or the resistance. And even if it is given as part of resistance, then it's possible to take this both in parallel and compute the equivalent resistance and then find out this. And if the friction losses are given, suppose 500 watts, then you'll have to minus the 500 watts here, and whatever value you would have got, this would have been considering the iron losses. So this is how it's possible to calculate the torque and the other parameters based on the equivalent circuit if it is given. So my output torque in this case will be equal to 58858, which is my P output, divided by my 2 pi ns. So this is equal to 58858 divided by 2 pi into 16.66. so this is a different machine which I have taken, and which was equal to 58858 divided by 2 into pi into 16.66. so this was close to 562 Newton meter, which you are getting this is close to 562 Newton meter. So this is what is your torque, and the torque which we found earlier, the starting torque and etc., was this torque which is available at the time of starting, but this is the torque which is available at the shaft based on what is my power available at the shaft. So this is my TS, its shaft torque, which is 56 point, and this torque has been found out based on what is my power available at the shaft, which has been calculated based on the power input. So that's all, and if you like this video, please do subscribe, like and comment.